Quick question. Lift acts on the wings. Agreed. But does it act at the same point on the wing throughout the flight? The answer is no. And that one fact explains more about aircraft stability than any formula you have memorized. Before we answer that, we need to establish 2 points on this aircraft. The first is the center of gravity, CG. Look at this aircraft. The engine sits at the front, fuel sits in the wings, passengers sit in the cabin, baggage sits at the tail. Every kilogram of this aircraft is spread across its entire length. Physics requires that the combined weight of all of it acts through one single point, shown here as the black dot on the fuselage, and that point is the CG. The aircraft rotates around CG in every maneuver, whether that is a climb, a descent, or a turn. CG is always the pivot, and here is something important that the exam tests directly. Loading changes CG position. Add weight to the front and CG moves forward. Add weight to the tail and CG moves back. Where your passengers sit and how your aircraft is loaded directly determines where CG sits on that day, on that flight. This is why every pilot checks the weight and balance before departure. CG position affects how that aircraft handles from the moment it leaves the ground. That is the first point. Now the second. The center of pressure, CP, the wing generates lift. You know that. But lift is not generated equally across every part of the wing surface. It concentrates, and the point on the wing chord through which the total lift force acts is called the center of pressure, shown here as the red dot on the wing. One important thing to understand right now is that CP is not fixed. It moves with angle of attack, and how it moves is the entire point of this episode. Here is the aircraft with both points shown together. The black CG dot sits on the fuselage with weight pulling straight down from it, and the red CP dot sits on the wing chord with lift pushing straight up from it. Two different points, two opposite forces, two different locations on the aircraft. Now, here is where the exam catches people. A question appears asking which force acts through which point. Under pressure, CG and CP look interchangeable because both are two letters, both are on the aircraft, both involve forces. Here is a way to keep them separated permanently. Look at the G in CG, picture that letter, and let it drop. Gravity pulls it straight down. Weight hangs below that point, pulling down toward the ground. G for gravity, pulling down. Now look at the P in CP. Picture that letter. It has a belly that faces upward. Lift pushes up from that point, straight toward the sky. P for push, pushing up. This is not a standard aviation term, it is a memory device. But once you see it, you will not mix them up again. And the most important relationship in this episode is this. For stable flight, CG must always sit forward of CP. That single relationship is what keeps the aircraft wanting to return to level flight after any disturbance. It will appear in the exam. Back to the question from the beginning. Does lift act at the same point throughout flight? Look at the aerofoil on the left. This is low angle of attack. Find the CP dot on the chord and notice where it sits, well back toward the trailing edge. Now shift your eyes to the aerofoil on the right where angle of attack has increased. That same CP dot has moved forward closer to the leading edge. The pressure distribution over the upper surface has shifted forward, and CP has moved with it. The higher the angle of attack, the further forward CP moves, and it reaches its most forward position, just before the stall. So the answer to our opening question is yes. Lift does change its point of application every time the nose moves. Every pitch input the pilot makes shifts where lift acts on the wing. There is one exception worth keeping in mind. On a symmetrical aerofoil, CP does not move with angle of attack at all. Everything we are discussing applies to a cambered aerofoil, which has an upper surface more curved than the lower. This is the standard wing section for most training aircraft. So CP moves forward as angle of attack increases. What happens when the pilot keeps raising the nose beyond that point? Look at the aerofoil on the left. where the wing is at a high angle of attack, and CP is near its most forward position. Now look at the aerofoil on the right. The pilot has continued raising the nose, and the wing has reached a point where the airflow on the upper surface can no longer follow the curve of the wing. It breaks away from the surface completely, and this is called boundary layer separation. When this happens, lift does not reduce gradually, it collapses suddenly. And CP, which had been moving steadily forward, jumps abruptly rearward in a single instant. That rearward jump shifts the entire force balance of the aircraft in a moment, pitching the nose in a way that makes recovery harder if the pilot does not respond immediately. That is stall. Not a gradual process, but an instant event. We have seen how CP moves and what happens at the extreme, but where exactly is it moving toward? There is a fixed reference point on the wing chord shown here as the blue dot, and it sits at 25% of the chord from the leading edge. It stays there regardless of angle of attack, regardless of camber, regardless of airspeed. It simply does not move. This point is the aerodynamic center AC. As angle of attack increases, CP moves forward toward AC, getting closer and closer, but CP never actually reaches AC before the stall happens. At the moment of stall, CP, which had been approaching AC, suddenly jumps rearward away from it. Four words that will answer more than one exam question. CP moves, AC does not. Everything we just said about AC sitting at 25% chord applies to subsonic flight. In transonic flight, that position shifts rearward, but that is a separate conversation for a later episode. Now that we understand how CP and AC behave on the wing, let us look at what happens when CG moves to the extremes of its permitted range and what that means for the pilot sitting in that cockpit. CG must stay within limits. The aircraft is certified for a specific forward limit and a specific aft limit. Look at the aircraft on the left. This is the normal CG position with the aircraft level and forces balanced. Now shift your eyes to the aircraft on the right, where CG has moved to the forward limit and the aircraft is nose heavy. Come to the tail and find the elevator there. It is deflecting upward, and that is the correct pilot input. The pilot is pulling back on the controls to raise the nose. But at the extreme forward limit, the elevator cannot generate enough force to overcome that nose heaviness. The pilot is doing everything right, and the aircraft is simply not responding enough. Forward CG makes the aircraft more stable but harder to control. More back pressure is needed throughout the entire flight, and stall speed increases because the wing must work harder to compensate for the nose heaviness. At the extreme forward limit, the aircraft may not be controllable enough to flare properly for landing. This is a controllability problem, not a stability problem. That is the forward limit. Now move to the other end of that envelope, and the situation changes completely. On the left, CG has moved rearward, and look at how close the red CP dot and the black CG dot now are to each other. As CG moves toward a CP, that gap shrinks, stability reduces, and the aircraft becomes progressively less willing to return to level flight after any disturbance. Now look at the aircraft on the right, where the aft limit has been exceeded. The nose is pitching up, and it keeps going. The pilot pushes forward on the controls, and nothing happens. The aircraft continues pitching up with no recovery possible. The aft CG limit is not a performance number like maximum takeoff weight or maximum speed. Exceeding those limits degrades performance, but the pilot retains control. Exceeding the aft CG limit takes away the pilot's ability to control the aircraft entirely. Never exceed the aft CG limit. It is not a performance limitation, it is a survival limitation. 5 questions, and everything you need to answer them is in this episode. Question 1. An aircraft increases angle of attack. CP moves A. Aft, B. Forward, C. Stays fixed. Q2. A symmetrical aerofoil increases angle of attack. CPA moves forward. B moves aft. C does not move. Q3. CG is at the forward limit. The aircraft is A. Less stable, harder to control. B. More stable, needs more back pressure. C. No effect on handling. Q4. For stable flight, CG must be A at CPB forward of CPC aft of CPQ5. Statement 1. AC is fixed at 25% chord. Statement 2. CP moves forward as angle of attack increases towards stall. A. Only statement 1 is correct. B. Only statement 2 is correct. C. Both statements are correct. Think carefully on Q5. The word toward is doing a lot of work in that question, and it is designed to make you second guess yourself. Question 1. B. CP moves forward as angle of attack increases on a cambered aerofoil. Question 2. C. On a symmetrical aerofoil, CP does not change position with angle of attack. Question 3. P. Forward CG increases stability but reduces controllability and more back pressure is needed throughout the flight. Question 4. PCG must be forward of CP for positive static stability. And that is the fundamental relationship in this episode. Question 5. C. Both statements are correct. AC is always fixed at 25% chord in subsonic flight, and CP always moves forward as angle of attack increases towards stall on a cambered aerofoil. CG, CP, and AC. 3 points, 2 forces, 1 relationship that determines whether an aircraft flies safely or not. Clear concepts, clear exam. See you in the next one.